This is Ms. Schultz, and I'm going to do 3 problems for lecture number 2 on related rates. So we left off here yesterday. Yesterday we did 2 classic problems, sphere inflating and the ladder problem. So this is a sort of, you try it on your own with the ladder problem. Let's read it together, and then you'll do it on your own and we'll go over it. The top of a 25-foot ladder, so I'll annotate as I go. The 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change in the distance between the bottom of the ladder and the wall? This is my question. What is the rate of change between the distance between the bottom of the ladder and the wall? So go ahead, pause the video, go through your, in a sec, go through your 5 steps. So you're going to start by identifying, I would start by drawing a diagram actually, and then write what is known, write what you need to know, write your relating equation, for it's the same as the last ladder problem, differentiate that, and then substitute and solve. And remember, at that substitution stage, you should be able to substitute for every single variable except for the one you're solving for. Alright, so I'll let you pause and go ahead and do that. Alright, and we're back. Okay, so here's the answer. The answer is D, 7/8. If you got that, you can move on, but let's go through it. So I got a 25-foot ladder falling down the rate. So this is X, this is Y. So the top of the ladder is 7 feet from the ground, but that's variable versus the 25 being constant. That'll come into play later. So my known, here's what I know. I know the ladder equals 25 feet. I know Y equals 7, but this is constant. And this varies, okay? This is variable. And then sliding down the vertical wall, so I know dy dt equals -3. This is what I'm looking for, this is what I'm finding. What is the rate of change of the distance between the bottom of the ladder and the wall? So dx dt equals question mark. Now my relating equation is x squared plus y squared equals 25 squared. The derivative is 2x dx dt plus 2y dy dt equals 0. Okay, now I'm going to substitute in. So 2, the x is, let's take a second here. The x, I look here and say, well, I don't know the x. Alright, so I'll leave it blank for a sec. dx dt is definitely a variable since that's what I'm solving for. dx dt plus 2, y is 7 at this instant, dy dt is -3, and this equals 0. So now I know I need to know x. So, so I need to be able to solve for x. I'm going to use the Pythagorean Theorem. I've already established that is the relating equation. I'm going to use that to find x. I know this Pythagorean triple. I could do 625 minus 49 is 576. Square root of that is 24. But I should just know 7, 24, 25. Triple. So this is 24. Okay. So this is 48 dx dt equals, so this would be a positive 21. 42 equals 42, so over 48, which simplifies to 7/8. Right? We need to divide by 6. Alright, so that's good. Alright, let's go ahead and do the next one. Now, there's going to be a visual I show you guys. Actually, before we do this visual, I want to show you, okay, so hopefully everybody's back. Alright, I want to show you the visual for a ladder. Alright, so sort of what we're talking about here. So let's go back here. Here is the visual. So here's what I want you to notice. I want you to notice that x and t are not changing at constant rates. Okay? So as I slide the ladder, so if you just, for instance, focus on one spot. So focus on right here and look at the rate of change. See if the rate of change is increasing or decreasing, because it's not going to be constant. Here, let me do it a little bit. So focus on this point going down and think about the rate of change. See how the rate of change, it gets quicker and quicker? So that's the point, is that my rate of change isn't constant. It's not sliding down constant. So go ahead, watch it. Slower, it's accelerating. Yeah, it's like it's accelerating. Okay, now the next time the letter's at the top, go ahead and look at your dx dt and see if that rate looks changing or constant. All right, so it's slower at the end. Actually, it does look pretty constant. Oh yeah, because so dx dt, however, is constant, and that's how we can say, yeah. So like one of the rates can be constant, but the other one's variable, and that's why you have to solve for it at a specific point. Because y varies in this exact one, I think in our last problem it was the opposite, but because y varies in this is why we need to say what's the rate of change when the ladder's 7 feet off the ground, as opposed to what's the rate of change in general, because you wouldn't be able to say that it varies. All right, so now let's, for the next problem, it's going to have to do with a boat winch. All right, here's a boat winch. So here's my boat, all right, and then here's my dock, all right, and for like really big boats, I suppose, not really sure, I've never really witnessed this in real life, but my boat is like it's kind of like a pulley, I don't know this pulley, it's pulling the boat in. So let's reel in. So this is my boat winch in action, bringing my boat to the dock. Okay, so here's the idea, is that this is turning at a constant rate. All right, this is turning at a constant rate. I'm just cranking it at a constant rate, not moving. And yet, dx dt is not constant, you'll notice. So like so focus on this point going this way. All right, and just watch it being reeled in and think about the rate of change. Do you see it accelerating? It's speeding up at the very end. Let's show the derivative so that you can actually see it. The derivative is actually going to be irrational. Yeah, so here's like the rope here. Okay, we're at this point of the derivative versus just like 2 feet more, and it's gone so quicker. So between 45, so here's 45 feet, okay, and here's 30 feet. See, like look at how it takes it takes a while to get that distance going on. All right, but then between 22 feet and 20 feet, it's super quick. So So the point is that excuse me, the point of this is that this rate varies. That's the whole point. And then I also wanted you to see the image of a boat winch. That's the other point. All right, so let's read and annotate this problem. So I have a boat whose deck is 10 feet below the level of the dock. So let's make some water here. Okay, here's my boat. Okay, the level of the dock. So here's my dock, all right? So this is 10 feet. It's being pulled by means of a rope attached to a pulley on the dock. So this says the pulley's on the dock. So we're picturing the pulley being here, and here's it being attached to the boat. All right, we're going to assume it's being attached to the boat at the bottom, equal to the water. All right, when the boat is 24 feet away, 24 feet away, and approaching the dock at 1/2 foot per second, how fast is the rope being pulled in? All right. So let's just go through this together. So I'll do an X and a Y. All right, so what's my knowns? So my knowns, I got Y equals 10. Now let's think, does that Y equals 10 vary or not? Let's actually pause there. Does the Y vary or not? It's like either it varies or it's constant. Let's go. All right, the Y equals 10 is constant. Okay, this dock does not move. That distance doesn't change. Now, I also know that X equals 24. So take a sec, think about if X being 24, if this varies or it's constant. So go ahead, think about that. Yeah, the 24 varies. So we'll represent it with a variable when the time comes. By the way, let's just do the third one. Let's do z. Does z, I don't know it yet, but does z vary or is it constant? All right, we're back. So this rope is being pulled in. The rope is getting shorter and shorter and shorter. So that z varies, okay? By the way, have you noticed that like last time we needed to find all three lengths? I propose we just do it right now. Let's just find z right now because we're going to have to know it. We can find it later, but we can find it right now. So take a sec, go ahead and find z. All right, let's go back in. I know my triples, so it's 5, 12, 13, so 10, 24, 26. Okay, so z equals 26. Let's take a second over in the margin. Let's write our triples down because it's going to be really helpful. All right, so our triples are 3, 4, 5, and multiples of that. So 6, 8, 10 is a Pythagorean triple, times by 3, so 9, 12, 15, times by 4 would be 12, 16, 20. Okay, so those are Pythagorean triples. The next one is a 5, 12, 13, and multiples thereof. So we had 12, 24, 26. I mean, you could have 15, whatever, you could keep going, but 7, 24, 25, and multiples thereof, so you could have like 14, 48, and 50, that was pretty rare, and then you have 8, 15, 17. So those come up a lot. You could have 16, 30, 34, that one comes up less. But these are the four Pythagorean triples that can just save you work. You know, I bet you didn't enjoy taking the square root of whatever 26 squared was, so it's out. All right, now for step number 2, what am I? Oh, I still have one more given though. I have a half, all right? And that half is approaching, so the distance between the boat and the dock is decreasing. So I'm going to label that negative a half, all right? I'm going to label that negative a half. Approaching the dock, and so it's approaching, the boat is approaching the dock, so that's a, think about what variable you'd represent that of. This would be dx dt. So rate of change in that horizontal distance there. All right. I got some animations to pop up here, so I'll just leave them out. Okay. So now, 2. What do I need to find? Okay. How fast is the rope being pulled in? How fast is the rope being pulled in? So think about what our find is. It's this. It's a dz dt. That's our find. Okay. So let's go ahead and use write our relating equation. So our relating equation, step 3, I'll say is x squared plus y squared equals z squared. All right. So go ahead. So now what's left is to differentiate and then substitute in and solve. Okay? And then write your sentence and sentence. Okay? So I'm actually going to leave a blank for you to write your whole sentence, and then we'll come back and we'll go through it. All right? Alrighty, and we're back. So let's see. So to go through it, oh, they had positive a half? Weird. Ugh. Really? Positive a half? I disagree with that. I disagree with this positive a half. Oh, okay. So let's make that negative. So this is what it looks like when you substitute in. So the 2.5 cancels, so I get negative 24. This is, so, well, I'll just do it myself. I don't like this animation. So I have 2x, which is 24. dx dt is negative a half, plus the derivative. So so I have 2x, so my relating equation, when I differentiate it, I get, for 3, my relating equation, x squared plus my y is a constant, so 10 squared plus z squared. So when I take the derivative, I get 2x dx dt plus 0 equals 2z dz dt. So my relating equation has that 10 in it, okay? My relating equation has that 10 in it. So now when I substitute in, it's 224 negative a half equals 2 times z, which was 26. Luckily, I already found that. 26. And dz dt is what I am solving for. Okay? So this is negative 24 over 52 equals dz dt. Okay? So negative, what is 4? So 6 over 13? So my sentence is the rope is being pulled in. So we know it's negative because like the rate is decreasing. We're pulling it in. Yeah, that's like the direction that I'm going. I'm pulling it in. So you could say for your sentence, but you don't need to, if you're saying pulled in, you don't need to use the negative also. If you did, I also wouldn't write it wrong. Doesn't matter. So the rope is being pulled in at a rate of 6, and that is feet per second. Feet per second. You could say at the moment when the boat is 24 feet away from the dock. Right? So the rope is being pulled in at a rate of 6/13 feet per second when the rope is 24 feet away from the dock. Right? The big thing is that this is a 0. Okay? Okay, great. Last one, okay? Last one. I'm going to read it from that here. I'll also make sure it's still recording. Great. Sand pours into a conical pile whose height is always 1/2 of its diameter. All right, this is already complicated. If the height increases at a constant rate of 4 feet per minute, at what rate is sand pouring from the chute when the pile is 15 feet high? Alrighty. So here's my thing. Okay, so height is always 1/2 of diameter. So I'm just going to write that. H equals 1/2 of d. Now, 1/2 of d is also known by another variable, yes? So I'm just thinking ahead. Equals radius is in radius. Okay. So height is equal to the radius always. Okay. So as my sand pours in, let me see if I have. Let me see if I have a demo of this. What? Okay. Let me see if I have a conical tank. Yeah. So this is just this is the opposite direction, but but let's fill this. So this is different dimensions. You can see my height is not equal to my radius. So it would have to be like a wider, but this is what's happening upside down. Instead of water flowing in, I have sand trickling upside down here. All right, so let's go back here. All right, so I have my diagram. Okay, if the height increases at a constant rate, so in terms of my knowns, so I'll just label it known. In terms of my knowns, I know that. I know height increases at a constant rate, so dH dt equals 4. All right, at what rate is sand pouring from the chute? Okay, so it's my find. Now what rate is sand pouring from the chute? Let's leave that away for a second. When the pile is 15 feet high, so I know H equals 15. So this is my kind of bugaboo. At what rate is sand pouring from the chute? So you might not really know that at first, so I'm going to get a little loose with the steps, and I'm going to say, like, I don't know how to label my find. I don't know, okay? I don't know how to label my find. So let's come up with a relating equation. So this, it's pouring into, this is kind of like the sphere one when it's going to be volume. Now, whenever you have a volume formula, you will always be given it. Okay, you don't have to memorize your volume formulas. You'll always be given it, even on the AP exam. And you'll be given it embedded in the problem, not on like some sheet up front. So that's extra nice. So volume equals 1/3 pi r squared h. Okay? So that's my volume. Now, in terms of what I need to find, since that's my relating equation, okay, aka step 3, I'm going to go back and use step 2. So I say, okay, I got r involved, I got h involved, but I don't have a v involved. So my find is going to have to do with a v. At what rate is sand pouring from the chute? So that is dv dt. Sand pouring is some volume. It's a change in volume. Sand pouring is a change in volume. But see how I like use my relating equation to go back and come up with my variable? Yeah. Alright, so now to take the derivative of this, I need to use a special rule. Alright, what's my special rule? The product rule. Yeah, in case you didn't think this was complicated enough. So here's my differentiating, also known as step 4. So the derivative of the left is dv dt. That's simple. Whew, derivative of the right. So this is my u, this is my v. Now the derivative of this is a constant. So do you see how I split this up? This is my u, that's my v. Okay, so this is 2/3 pi r to the first power times dr dt. Go ahead and take the derivative of h, dh, dt. Alright, so now my dv dt, I'm going to actually write this a little bit lower to give us some space. So now my derivative, dv dt equals, what? This is crazy, 1/3 pi r squared dh dt plus, those multiply together, okay, 2/3 pi r h dh dt. Again, order doesn't matter, multiplication is commutative, but this would be like a good standard way to do it. Yeah, so this one, you have to use the product rule. There's two different variables. Whenever there's either the same variable in more than one spot, okay, or definitely two different variables, you gotta use the product rule. Now I'm gonna substitute in. So I know dv dt is what I need to find. So here, this is in fact going to stay varied. Okay, so this is step 5, sub in and solve. So dv dt equals. Now, so in theory, I need to know all of these things. Alright? So take a second. Substitute in, so you should know what they all are. You should know what r is, you should know what dh dt is, you should know what r is, you should know what h is, and you should know what dh dt is. Yeah. And substitute them all in, and then you just simplify and go from there. So I'm going to have you this time just input your answer as a number instead of a sentence. So just get what dv dt is. Actually put the label too. So here's how I want you to input your label. So as the number and with a label. So it's change in volume over change in time. So think of what the label and volume is per time. All right, and we're back. So let's go through it. 1/3 here. I can tell you the answer real quick, so if you know you got it right or not. Let's see, 900 pi. So if you got 900 pi, good job. You solved your first one with the product rule. Kind of a big deal. Kind of a big deal. First really right from the product rule. So r, since r is the same as my height, since my height is half my diameter, if I know my height is 15, I also know that's my r. So 15 squared, dh dt is 4 plus 2/3 pi, 15 times 15 times 4. Alrighty, so let's do that out. 225, well I could just multiply this. So this is 15 times 15, this 15 is going to make a 5. So 15 times 5 is 75, 75 times 4 is 300. I did that right? And then here, I'm going to also take a third of one of these 15s and make it a 5. As a 75, 75 times 4 is 300. 300 times 2 is 600 pi. Yeah, so that's how I get my 900 pi. And my units are feet cubed per minute. Okay. Woohoo! So you could say, if you're writing a sentence, you could say the sand increases, or the sand, I would just use the word volume, okay? There's no reason to be cryptic about it. The volume of the sand pouring from the chute increases at a rate of 900 pi feet cubed per minute. The volume of the sand pouring from the chute increases at a rate of 900 pi feet cubed per minute. If you want to be really good, like you can say when the pile is 15 feet high. It'd be like extra. Awesome. All right, thank you so much. Bye-bye.